Well, we heard before several introductions to quantum entanglement. Here, I just would like to stress a point, and is that what it was seen at the beginning, like an strange phenomenon that was questioning the completeness of the theory, so somehow like some kind of menace. Then it became an opportunity with the emergence of quantum information because entanglement is in the basis of all the applications of quantum information, such as cryptography and so on. So somehow what it was a threat became an opportunity. So we are here because we hope that perhaps the same could happen with when applying this entanglement analysis to LHC physics. It could provide a new way to analyze or to extract information from LHC data. For example, we saw in the previous case a motivation to analyze a particular channel in Higgs decay, and the other way around. LHC data could perhaps provide new ways to test principles of quantum mechanics. Okay, so the physical consequence of entanglement, that is perhaps that departs more from physical intuition, is the violation of Bell inequalities. That is impossible in a local realistic theory. So this is the operator that you have to consider in a case with two parties with two outcomes. So we know very well the CHS inequality. Here you have a picture on one of the papers by these authors. So as stressed by Alan Barr in one of in his talk and in his paper, this looks too much to a situation that we have seen in particle physics at the LHC, that is the decay of a Higgs, a scalar, into two vector bosons. So, and there will be we have also several talks about that for both Z and W bosons. And there has been many papers about this subject. So as I mentioned before, this work is based on this article. So the main goal of this talk is just to explore, to explore inequalities in Higgs going to ZZ in the leptonic channel. That has one advantage. The advantage is that reconstructing the set is very easy, and identifying leptons at the LHC is very easy. What is in principle disadvantage is that the cross section is small compared to other cases. So let's assume a particular event of a decay of a Higgs into ZZ. So in principle, one of the two sets has to be, at least one has to be off cell. But we could work in the center of mass reference frame and then fix the axis of the momentum of the set bosons. And then this particular event, the kinematics, is just fixed by the two invariant masses of the two set bosons. And then once the momentum, okay, is fixed by these values. Of course, the conservation of spin, of angular momentum and parity implies that among the 9 possible combinations of spin, only these 3 particular combinations appear that corresponds to a JZ equal to 0. If you also take into account parity, then you get this particular shape where these two have to be equal. And that one, in principle, is different, and this is related to the fact that an axis is selected in this event. In the case where this momentum is 0, so where the two masses just saturate the MH bound, then you will get some kind of additional spherical symmetry. So then from the Lorentz structure of the vertex, you could reconstruct that particular state, okay, using just the polarization vectors or the helicity amplitudes. And then you get that the V value can be written as a function of the two masses and the mass of the Higgs. Of course, V has to be larger than 1, and that corresponds to the fact that that K, well, it's the other way around. The momentum has to be larger than 1, and then beta has to be larger than 0, and then beta has to be larger than 1. Okay, this is once you get the state, you could evaluate for that particular state the density matrix. So here you have the density matrix, and depends just on that parameter beta that I was mentioning before. Of course, the quantum state of the 2Z is not going to be a pure state like that one. It's going to be a mixed state. And the nature of this mixed state is shaped by the kinematics. So if you know what is the distribution of this beta parameter, that mainly is just telling you how is the kinematic of the decay of the Z boson, then you could reconstruct, you could evaluate the raw matrix. So this is in comparison, for example, with a much more complicated cases like the top. If you, for example, have a pair of top quarks produced at the LHC, what is the origin of the fact that you are in a mixed state? Is due first to the fact that you have two different production channels corresponding to QQ and gamma gamma. Is due to the fact that the kinematics of the initial channels vary, that is controlled by the PDFs of the protons. Then this is modeled by the symmetries of the problem. The symmetries of the problem are gauge symmetries, could be also global symmetries, and also the Lorentz structure of the vertex. And then finally, at the end, the mixed state of the fact that it's a mixed state is also controlled by the different kinematic of the final state. So you have to add all these like 3 different layers. Here you only have 2 layers. That is the structure of the vertex. That is the simplest one because it's just a scalar coupling to 2 vectors, and then the kinematics is the kinematic of a particle that is the Higgs. In a very good approximation, if you consider that one of the Higgs of the Z bosons is on shell, is the kinematic of a 3-body decay. So you could evaluate that by hand. So if you are bored one of these days, I hope you don't, then you could just sit down and evaluate that analytically. So this is a case where you can calculate from the very beginning what is your density matrix for this state, and then you will get that result. And notice that now you have 2 parameters. Why you have 2 parameters if previously we only have 1? And this is because because the expected value, so the average value for beta to the square is different to the square value of beta. And here in the past you have all these. Previously you had, remember that you had, these 2 b and beta squared, these 2 terms. Okay, so now we have seen what kind of density matrix we expect from a kind of symmetry analysis. And then we have to do now is just to reconstruct this quantum state. The process of reconstructing a quantum state from several measurements from an ensemble of different copies. This is quantum tomography. Well, there are 2 points that are important. One is just you have to choose a basis for rho in order to do that, and you have to express the experimental measurements of that that you could do on that states as a function of the expansion parameters. Of course, if you choose a convenient basis, convenient means that let's say that has the symmetries that is compatible with the symmetries of the problem, for example, then your quantum tomography could be optimal. In our case, a way to parameterize this 9x9 spin density operator, we have chosen a basis of 9 matrices that are the identity that takes care of the trace of the raw matrix, and then we have included the 3 angular momentum L = 1 matrices, and then some symmetric products that are written here with a particular value of the 3rd component of the spin that is written here. An alternative to that, of course, could be take the Gell-Mann matrices as is done in other particles, but we think that things are easier in that language. Of course, they have to be equivalent because it's just another parameterization, but the extraction of the components, I think, is cleaner. Here you have the raw matrix expressed as a function of these matrices, and then you have the polarization vectors here, and that will correspond to the correlation, to the spin correlation among the two set bosons. So here you have the total number of components. This is the form of the. At the end, we are considering two different pair channels, so muons and electrons, so different leptons. And this is the differential cross-section that, finally, the differential cross-section is nothing but unobservable. So we should be able to express this observable like the trace of rho times some operator. The operator that go here, of course, you know, is the decay density matrix, and is evaluated here for the case of a set boson or decaying into leptons. It's just, theta is the angular respect to the momentum of the set, and the azimuthal, and phi is just the other angle. An extra parameter appears here that is eta L, that for the case of the W, this parameter is 1 or -1, and reflects the fact that you are in a theory that couples uniquely through left-handed interaction. Here there is a mixture of both, so this parameter is smaller in that case. So using that, you could decompose this matrix, just tracing into the previous matrices, and then what you get is some terms that are proportional to the harmonical spherical harmonics. Sorry, and this is because we have used a basis that has good properties concerning SU2. So in that way, it is very easy to extract the vector polarization and the correlation just by doing this integral. So just by projecting out with the spherical harmonics. In fact, this method could be very easily generalized. When I say generalized, I mean that you could do that not just for a particle that decays in two, but for two particles that came from a general scattering, for particles that have different spins, not just 1 and 1 or 1 and a half, or even for an state that is described by 3 different particles. So this procedure will generalize, and it will be very easy to extract the coefficients just applying this kind of techniques. So you will have, for example, you have three particles, and you want to study three particle correlations. Then you should extract the information with 3 spherical harmonics. And this method is explained very well in the article by Alexander Bernal that is shown here. And this is an alternative method to what Alan was explaining the other day with the Q symbols and the Wigner P and Q symbols. So at the end of the day, what we get is that the raw matrix has this shape. Notice that we have 3 coefficients now, and we started with a matrix that in a state that have 2 parameters. Then there should be some kind of bound, let's say, or some kind of one of the parameters should be written as a function of the other ones. And this is the constraint that you get when you make this kind of expansion. We are not imposing this constraint when extracting data because we think that it's more interesting to use it as a way to estimate the uncertainties from the experimental point of view. Okay. So a comment on entanglement, because we want to know if the state described by this raw matrix of the 2Z is entangled, and if it is could be used to show the violation of the Bell inequalities. So in order to check if a system is entangled, you have to check if it is possible to write as the product of 2 different raw matrices, density matrices, for the 2 subsystems. In general, this is very complicated, but we know that, Perez and Horodetsky show that a sufficient condition is that the raw matrix, if you build the transpose matrix and this transposing in just one of the two indices, let's say Bob, then if this matrix has a negative eigenvalue, then this is a necessary condition. For a general density matrix that with vanishing third component, that it would be the case for a Higgs decaying into two vector bosons, so not just for ZZ, also that would be also valid for decaying into WW. If you build this transpose matrix, and then you could see that the state is entangled if one of the non-diagonal terms is different from 0. And in fact, in that case, it's not only a necessary sufficient condition, but it's a necessary one. So, and as I mentioned before, this is relevant not just for the Higgs Z decays, but also for WW1s. Okay, so in our case, that translates into the condition that the quantum system is entangled if one of the two coefficients of these two correlations is different from 0. So what about Bell inequalities? So there is a subtle point that we learned before, and is that since we are dealing with Q-tricks and not with qubits, the generalization of the CH inequality now is the CJL-MP inequality. So you have to take this particular combination. So one of Alice and Bob have these three states, and you have to, the first term is the case where Alice, the first measurement by Alice and the first measurement of Bob is the same, and you have all these terms that are, these equalities are modulo 3. So this inequality could be, of course, written in terms of a Bell operator that depends on this unitary matrix, because since we are fixing the outcomes, the operator is given just by the rotation matrices that diagonalize that operator. In the case of in the case of a singlet state, it was the optimal operator was evaluated long time ago and is known to be that one. Notice that this state, so this is not our state, this is a maximally symmetric one with all the coefficients being the same, is invariant under this rotation, this unitary transformation you start. In our case, we have a minus symbol here, and these two outcomes are interchanged, but that you could rotate just using this matrix. And in fact, you still have the freedom. You still have the freedom to rotate it with these U matrices. And we have seen that the optimal operator is that particular one in our case. So with this improved operator, you could evaluate the Bell inequality, and is better. This has a better behavior for different values of B. So in particular, since we are picking in that area, this is better than a version in which you don't rotate. So in terms of the spin polarization correlation, this is the expression. And now, finally, numerical results. So we have generated, we're using MathGraph and implementing in the final step I was mentioning before, the analysis of Higgs decaying into the 4 leptons. The branching ratio for this process is 10 to the minus 4. So some technical details that, well, the orientation is the typical one, so I'm not going to repeat here. The cross-section is 48.6 picobars at the center of mass. Well, taking into account the branching ratio is reduced to that value, 6 femtobars. Where we have assuming a lepton detection efficiency of 0.7, so 0.5 for 2 leptons and 0.25 for the ensemble of 4 leptons. This is the assumed luminosity for both the LHC runs 2 and 3 and the high lumi. And in order to evaluate the statistical uncertainties, we have done an ensemble of 10 to the, 1,000 pseudo experiments, and I will present the results with and without cuts on the mass. For the For the case of run 2 and 3, this is the value that we get for the two coefficients. Remember that the entanglement is obtained, or it is shown when these coefficients are different from 0. So you could see here that once you make harder cuts on the lower invariant mass of the set boson, then these values are getting larger. In particular, they should be approaching to -1 or to 1. Okay, and this is the value of the Bell inequality. Okay, so the result is that entanglement could be shown at the 2 sigma level, and the Bell inequalities well is less than that. For the prospects, of course, for the high Lumi data, since you have 10 times more data, so 1 over square root of 10 is more or less 3. So the error is reduced by a 3 factor, and the central values, of course, they are quite similar. The result is that entanglement could be shown at the 5 sigma level, and the Bell inequalities will be evaluated at a similar value. So just a brief comment about new physics. If you put some new physics in the vertex, so instead of considering just that term, that is that appear in the standard model at 3 level, you will induce, you have to consider these two extra pieces. The third one is the one that violates CP. The previous results could be easily generalized because the entanglement analysis that we have done, the condition is valid also for cases where the only thing that you would have used is the conservation of the third component of the spin. So this is going to be the case. And the optimal Bell operators now will depend on these two coefficients. So that brings me to my conclusions. So LHC data offer a good opportunity to test Bell inequalities at high energies. The quantum state of the set pairs is a great system, and it's very easy to understand, and it's very easy to have some kind of theoretical or intuition or how this is going to be produced, and how and you could, as I mentioned before, you could even evaluate this matrix analytically. So this is the result that we get, that using run 2 and 3 data, you could show, well, the entanglement is only proven at 2 sigma level, but if you with the data provided by the high Lumi LHC, then the entanglement could be proven at 5 sigma level, and the Bell inequalities at least at 3 sigma. So the relevant aspects, I would like to comment to relevant aspects as that in order to improve the quantum tomography, a careful choice of raw matrix could help. And also it's important just to optimize the Bell operator. So thanks for your attention.
Thank you very much for the very nice talk. Questions to Jesus? I had one actually. So you mentioned that this is a mixed state. I always thought somehow when you look at the Higgs, if you boost to its like rest frame, you can look at it as a pure state of because of its spin 0. I mean, what makes it to be a mixed state? What is the?
Yeah, because your state, well, if you have a look at the, let's say, at the, imagine that you have produced the set and the 2 leptons. So what is the state is described by the spin of the particles, but also by the different momentum of the particles. So the fact when you are ignoring the momenta, because you are dealing in data with different invariant masses of zeta, of Z, so you are combining. It's like you are tracing in momentum. This is what you are. You are like tracing in this parameter beta that I was showing before.
A follow-up, thank you very much for the nice talk. A follow-up on that is that I guess it's not absolutely strictly necessary to integrate over those different betas. Our experimental colleagues quite often split things up into different regions and analyze them in parts. And so one could slice it up and analyze each part of it and then get an overall p-value that comes from the combination of those
Yeah.
p-values and get a slightly improved sensitivity this way as well, I think, if one were
Yeah.
willing to do it.
You are right. In fact, this is more or less what we are doing here when we choose, and when you impose a cut, let's say you are slicing a particular values for the, you are choosing a particular kinematics, and then what you are doing is that you are producing, let's say the Z boson close to rest. This is what is giving you a more symmetrical state, and you know that the more symmetrical state is the one that has a highest value of entanglement. So this is why by doing this kind of cuts, you are improving the results. But yeah, you could think that the raw matrix, in principle, well, you could decide what you are putting inside there. So you could just choose a particular value. Yeah. The point here is that the statistics is not very large due to the smallness of the coupling of Z to lepton. So you are on the verge of having a large error. So
yeah, so the limiting factor here is actually the statistics. So let's say the low cross section times the branching ratio of the Higgs, and not the backgrounds, for example, right? Because the backgrounds here should be very small. If you have 4 leptons, maybe just dibosons, but still. More questions? There is Marcel.
Yeah, I was wondering about the statistics. In fact, if you focus on the cleanest channel, which is 2 electrons and 2 muons, but you could easily get a factor 2 by looking at 4 electrons and 4 muons as well. I think it should be easy enough to produce the Z candidates and get the correct pairing. It is a complication, but I think it's feasible. Have you looked into that at all?
yeah, well, as you mentioned, the point is there that you have an ambiguity in the pairing of the similar because you are the same kind of leptons in the 2 channels. This is a complication. Also, the raw matrix will be a little bit different, I think. Yeah.
Okay. Yeah, we'd have to check with experts on this, but I think in practice with a Z mass constraint, well, one of them is soft shell, of course, but at least one you get pretty precise, I would think.
Okay. Thanks for the comment.
I have one question on your Monte Carlo study. Did you take into account the detector acceptance? I was missing this point on your slide that you only mentioned the lepton detection efficiency. I wonder about PT and eta cuts.
Well, I think that since we are assuming this detecton efficiency for leptons, and in principle, this is the only thing we are doing. So
then I think it's a good idea if you check that the event yields that you have in your follow-up slide actually match the published CMS and Atlas result for run 2. I believe this acceptance will be an effect that may be a real factor 5 or 10 decrease in event statistics. Because what my experience is that stuff is usually you lose 1 lepton out of the tracking acceptance because at least one is quite highly forward usually. That's my experience in Taos, that there's a real suppression factor in your event statistics. It's not a 10 or 20% effect, but it may be a factor 5.
So in principle, we have not done a full detector simulation, but I don't know what would be the correction to that. No, that I don't know. I don't know if. Okay, we will see. Thanks.
Sorry for a very naive question. So I understand this beta depends on the absolute value of the momentum, not in the momentum, right? That's the only thing, right? Is there any, the previous question, is there any clean way to select particular momenta, values of the momenta?
Well, in principle, yes, because you are reconstructing the two Z bosons.
Right. Okay.
So in principle, the point is that if you start selecting particular slices, then you are reducing the number, the data,
The data,
and then
yeah.
the error gets larger. So it's some kind of compromise. Going to the region with the two set bosons are almost at rest, that would be the more interesting region from the point of view of entanglement and their inequalities, but you are reducing the number of.
So have you performed this trade-off analysis, like trying to find the best window or that? Like pre-selecting the beta, so that because
You could do that. If you do that, the region that you will get will be that region that is close to one, because as well, I think Jose Ignacio was mentioning before, the optimal operator for the singlet is not the one that produces a larger violation of the Bell inequality on other state that is not symmetrical. So
Correct,
that is not
correct.
fully symmetrical. That is like something amazing, but it's like that. So this is shown here. So in fact, the Bell operator that we are considering is even more convenient for this kind of events. So it would be better to choose, let's say, some kind of momentum in the set direction rather than zero momentum. So this is the value.
right, but this is for a particular Bell inequality. Thank you.
Yeah.
Just about the, why do you have the uncertainties going up as you move up the cut? Because most of the events are at the end of the cut, no? Is the
No,
next to the last
yeah, but-
slide, I think.
What you are doing is just so in the first case there are no cuts. So
No. I'm thinking the slide where you put the.
Yeah, but it's like cutting here in beta. So no cut, you are dealing with all these events. Once you start putting cuts, then you are taking only the part that is on the left of the point where you are making the cut somehow.
Most of the events are there, right?
Yeah.
The events are close to the thread.
So you are telling me what is the speed at which this value?
If you just keep the events close to the thread, most of.
But you have to know where is the cut in that figure. So let's say that already these particular cuts. Well, you could see here what is the effect on the number of events. So if you put a cut on 30 GB, you are losing 1/3, 2/3 of the events. So
I would have expected you have like a big nerve. No, like an exponential. So, okay.
So this information is provided here, yeah.
Okay, no, I didn't see that.
So let's say that a linear change in the cut is not producing a linear change in the number of events. Yeah, sorry. Yeah.
Thank you.
Okay, we had a very nice discussion, so we can thank Jesus again. Going now to the last talk of this session.